I'll go over the proofs for two short theorems used in multivariable vector calculus. The first one is the divergence of a curl is zero, and the second one is the curl of a gradient is zero, and more specifically, the zero vector, because curls output vectors. So the proof are as follows. For the first one, we have P, Q, R, and they are scalar value functions. PQR has continuous second order partial derivatives. Okay, and then we have the vector value function f of x, y, z, and this is going to equal to p of x, y, z. Now these are multivariable functions. Okay, q of x, y, z, and r of x, y, z. Okay, so p, q, r are simply the coordinate functions for f. Okay, now this implies that I need to take the curl of f, okay, which is actually the gradient or the del symbol or the nabla symbol, cross product with f. And some people, they add the arrow on top of the gradient symbol, which is fine. Okay, so this is actually curl of f. And this is equal to, we're going to take the determinant now, ijk, okay, the standard unit vectors for R3, 1, 0, 0, 0, 1, 0, 0, 0, 1. Now I'm going to take the gradient vector, which is just the vector that consists of the operations, the partial derivative operations, as its coordinates. Okay. And then little f vector would be, I'll just write it as p, q, and r. Okay. Taking this determinant, I'll get I times partial r over partial y minus partial q over partial z. And then minus j times partial r partial x minus partial p partial z plus k times partial q over partial x minus partial p over partial y. All right, and this is going to equal to, let me just combine it into a vector form again. It's going to be partial r over, let's just copy and paste this. And then for this one, I'll actually have to change the order because of this negative sign over here. Okay, so then I'm going to have to switch these around. Okay, and then finally, I have this. Cool. All right, and now I got that. Now I'll need to take the divergence, which is actually gradient vector dot product with this result right over here. Okay. And by the way, this is actually just equal to the divergence of my curl. Of f. Okay? So now, what this is going to be is that this is going to equal to, well, I guess I'll write it out fully. Partial x, partial y, partial z, and it's going to be dot product with this over here. Move this up a little, okay. All right. Let's see what this is equal to. All right. So I'm going to have partial squared r over partial x partial y minus partial squared q over partial x partial z plus partial squared p over partial y partial z minus partial squared r over partial y partial x plus partial squared q over partial z partial x minus partial squared p over partial z partial y. And this is going to equal to what? Okay, so notice right here that the reason why I added this part, that p, q, and r having continuous second order partial derivatives, so that we could have symmetry of the second order partial derivatives. Schwarz's rule, right? Schwarz's theorem. Okay, and we have it where that these two are the same. Okay, partial x partial z on the denominator, or partial z partial x on the denominator. These two are actually the same. Okay, so they will cancel each other out right over here. Okay, so then what else do we have? We have these two are going to be the same, and then we have that these two are going to be the same because of Schwarz's theorem. Okay, so then at the end of the day, we're going to get the number 0. And that completes the proof for this one. Now, the proof for the second one is as follows. Okay, so we're going to have the scalar function f. It has continuous second order partial derivatives again, because we're going to utilize Schwarz's theorem later on. So this implies that if I take the gradient of f, then this is equal to partial f, partial x, partial f, partial y, partial f, partial z. Okay, and this implies that the cross product of the gradient vector with the gradient of ff, but this is actually equal to the curl of the gradient of f. So with the cross products, we again need to take the determinant of a 3 by 3 matrix, okay, then we have gradient of f and what is this equal to? It's equal to I times partial squared f over partial y partial z minus partial squared f partial z partial y minus j times partial squared f over partial x partial z minus partial squared f over partial z partial x plus k times partial squared f over partial x partial y minus partial squared f over partial y partial x. And again, because f has continuous second order partial derivatives by Schwarz's theorem, these two are the same, these two are the same, and these two are the same. So ultimately, I'm going to get 0i minus 0j plus 0k, okay, which is just 0, 0, 0. that is equal to the 0 vector. Okay? And this completes this proof.